Welcome back to AI Academy. In this series we are learning about Python for data science. In our last lecture we have explored about Python control structures and functions, and we have seen the modular way of transforming data for better readability. In today's lecture we will discuss about exploratory data analysis. So here we will dive deeper into the dataset we've been working with, starting with a look at frequency tables and two-way tables. These are great tools for beginning to understand the patterns in our data. Next, we'll explore how to extract joint probabilities from these two-way tables. Understanding joint probability is key to grasping how often two events happen at the same time within our dataset. We'll also cover how to calculate marginal and conditional probabilities using the same tables. This will help us see not just the relationship between two variables, but also how each variable behaves in the context of the other. Finally, we'll discuss a concept called correlation. While most of what we've covered today focuses on categorical variables, correlation is crucial when we start dealing with numerical variables. It's all about measuring how closely two variables move in relation to one another. By the end of this lecture, you'll have a toolkit of methods for analyzing both categorical and numerical data, helping you to uncover and understand the relationships within your data. Let's get started. Alright, let's dive into how to create a frequency table and why it's a crucial tool in our exploratory data analysis toolkit. But first, what exactly is a frequency table? It's a way to see how often each category within a variable appears in our dataset. This helps us understand the distribution of categories and begin to analyze relationships between variables. Imagine you have a dataset with multiple variables and you're curious about the relationships among them. It's not practical to examine all variables at once, so we tackle them one by one. For instance, we can explore the relationship between categorical variables using cross-tabulation. If you're focusing on just one categorical variable, a frequency table is your go-to method to analyze it. The command used is the pd.crosstab, is a function from the pandas library in Python to create a frequency table, which counts the occurrences of each category within a specified column of a data frame. Here's a breakdown of what each part of the code does and how the output is generated. pd.crosstab function is used to compute a simple crosstabulation of two or more factors. It is very useful for summarizing data to observe relationships between categorical variables. Index equals fuel type parameter specifies the index of the resulting table. Here, it uses the fuel type column from the data frame. Each unique value in this column will become a row in the resulting table. Columns equals count. Normally, the columns parameter can be used to provide a second variable to form a two-dimensional table. However, when you use count as the value, pandas doesn't treat this as a column from the data frame but as an instruction to count the occurrences of each unique value in the specified index. Drop NA equals true parameter tells pandas to exclude any rows from the data frame that have missing values in the fuel type column. This ensures that the frequency count only includes valid data. So, the output is a data frame with the counts of each unique value in the fuel type column. Each row label corresponds to a unique value found in the fuel type column of the data frame. In this case, there are three types: CNG, diesel, and petrol. The column 0 is an automatically generated column name by pandas, since no specific name was given for the count column in the column's parameter. It represents the count of occurrences. And the values, 15, 144, and 1177, represent how many times each fuel type appears. For instance, CNG appears 15 times, diesel appears 144 times, and petrol appears 1177 times. We can see that most cars run on petrol, a few on diesel, and even fewer on CNG. This frequency table is very helpful for understanding the distribution of categories within a single variable in your dataset, which can be crucial for exploratory data analysis, especially when preparing data for further statistical analysis or modeling. This approach lets us clearly see the distribution within one variable. But what if we want to analyze the interaction between two categorical variables? We can add another variable to our crosstab and examine their relationship further. This way of analyzing data helps us to not only understand the frequency of categories but also how these categories relate to others in our dataset. Alright, now let's explore how we can analyze the relationship between two categorical variables by using two-way tables. In this example, we'll look at the relationship between gearbox and fuel types in cars. Previously, we focused solely on the distribution of fuel types, but this time, we'll dive into how gearbox vary with different fuel types. Gearbox types in our dataset are categorized into two groups, manual and automatic. These are represented in our data with a variable named automatic, where 0 indicates a manual gearbox and 1 indicates an automatic gearbox. To create a two-way table that shows this relationship, we'll use the pd.crosstab function from pandas. The code you provided uses the pd.crosstab function from the pandas library to create a two-way table, which cross-tabulates two categorical variables from a data frame to show the relationship between them. So, in this case, the syntax, index equals df1, automatic, parameter sets the rows of the resulting table based on the automatic column in the data frame. This column represents whether a car has an automatic gearbox represented by 1 or a manual gearbox represented by 0. Columns equals df1, fuel type, sets the columns of the table based on the fuel type column. Each unique value in this column will form a separate column in the resulting table. And the output is as a two-way table. The row labels represent the values found in the automatic column of df1. The label 0 likely represents cars with manual gearboxes, and 1 represents cars with automatic gearboxes. The column headers are the unique values from the fuel type column, showing the types of fuel used such as CNG, diesel, and petrol. Each cell in the table shows the count of cars that fall into the corresponding combination of gearbox type and fuel type. For example, there are 15 cars with a manual gearbox that use CNG, and there are 144 manual gearbox cars that use diesel. Interestingly, there are no automatic gearbox cars that use CNG or diesel, and all 73 automatic cars use petrol. This pattern tells us that automatic gearboxes are predominantly found in petrol cars, with very few or no automatic options available for CNG or diesel cars. This type of table is incredibly useful for understanding how two categorical variables interact. For instance, from this output, you can infer that cars with automatic gearboxes in this dataset are only available with petrol engines. This information can be vital for market analysis, product planning, or even customer profiling, offering clear insights into the combinations of features available in the dataset. Take our analysis a step further by converting the numbers in our two-way table into proportions. This conversion is what we refer to as calculating joint probabilities. But first, what exactly do we mean by joint probability? It's the likelihood of two independent events happening simultaneously. For example, the probability of a car having a manual gearbox and using CNG as fuel. To calculate these joint probabilities using our two-way table, we'll continue using the pandas pd.crosstab function, but we'll add an extra parameter, normalize equals true. This parameter changes all the numerical counts in the table into proportions of the total, giving us the joint probabilities across our categories. With this adjustment, the output of our table now shows proportions instead of counts. Let's look at how to interpret this output. There is about a 1.12% chance that a randomly selected car from the dataset is manual and uses CNG. There is about a 10.78% chance that a car is manual and runs on diesel. There is an approximately 82.63% chance of a car being manual and running on petrol. This suggests that manual petrol cars are the most common type in this dataset. There is a 0% chance of finding a car that is automatic and uses either CNG or diesel. This indicates that all cars with automatic gearboxes in this dataset run on petrol. There is a 5.46% chance that a car is automatic and uses petrol. These probabilities offer insights into how certain behaviors, based on gearbox type and fuel type, co-occur within the dataset. As they give us a clearer picture of the relationships and trends within our data, showing us not just how variables are distributed, but how they interact with one another in real-world terms. This kind of analysis can be especially useful when making decisions based on the likelihood of certain combinations occurring, like planning production lines or targeting marketing for specific car models. Keep in mind that these interpretations are based on the current dataset and could vary with different data samples or over time as trends shift. Now, let's move on to understanding how to calculate marginal probabilities using our two-way table. Marginal probability refers to the probability of a single event occurring, without considering the influence of other variables. This is particularly useful when you want to understand the standalone impact or occurrence rate of one variable across different contexts. To calculate marginal probabilities, we'll still use the pd.crosstab function in pandas. However, we'll add a couple of tweaks to the parameters to get the probabilities in the format we need. Here, normalize equals true converts the table values into proportions, and margins equals true adds row sums and column sums to the table. These sums are the marginal probabilities, showing the total probability distribution across either rows or columns, irrespective of the other variable. Let's break down the output. Rows representing gearbox. 0 represents manual. The marginal probability of a car being manual, regardless of fuel type, is 94.54%. 1 represents automatic, and the marginal probability of a car being automatic, regardless of fuel type, is 5.46%. And columns representing fuel type. The marginal probability of a car using CNG, regardless of gearbox type, is 1.12%. The marginal probability of a car using diesel, regardless of gearbox type, is 10.78%. The marginal probability of a car using petrol, regardless of gearbox type, is 88.1%. The sum of all probabilities in the table equals 100%, which is expected as it represents the total probability space of this dataset. By setting margins equals true, the output table not only shows the joint probabilities such as how likely two specific events can occur together, but also these marginal probabilities, giving a more comprehensive statistical view of the data. This total picture, where the sum of all probabilities equals 1, ensures that we're accounting for all possibilities in our dataset. Now, let's discuss about calculating conditional probabilities using the two-way table. Conditional probability measures the likelihood of an event occurring, given that another specific event has already occurred. It helps us explore dependencies between variables more deeply. To calculate conditional probabilities with pandas, we still use the pd.crosstab function, but we'll adjust the normalization parameter to focus on one variable at a time. This setup allows us to understand the probability of one event based on the occurrence of another. In this function, setting normalize equals index normalizes the data across each row, each type of gearbox, so the probabilities in each row sum up to 1. This setting is essential for calculating conditional probabilities correctly. Let's interpret the output, rows representing gearbox. 0 represents manual gearbox for which the conditional probabilities for each fuel type given that the gearbox is manual are, as follows. CNG, 1.1876%. Diesel, 11.4014% and petrol, 87.4109%. Whereas 1 represents automatic gearbox, the conditional probabilities given that the gearbox is automatic are CNG, 0%. Diesel, 0% and petrol, 100%. So, 87.41% of the manual cars use petrol, 11.4% are using diesel and 1.19% are using CNG. This suggests a diverse range of fuel options for manual transmissions. And 100% of automatic cars in this dataset are exclusively using petrol. This indicates a limitation or specific design choice in the dataset where automatic transmissions are only available with petrol engines. By analyzing these conditional probabilities, we can make informed guesses about fuel types based on gearbox configurations. It's a valuable insight for stakeholders in automotive industries, helping to tailor their product lines or marketing strategies to the most likely combinations of features found in cars. Next, to explore the relationship from another angle, for example how gearbox types vary with different fuel types, we adjust our conditional probability calculation by normalizing across the columns of our two-way table. This adjustment helps us understand the probability distribution of gearbox types given a specific fuel type. In this setup, normalize equals columns ensures that the sum of each column is 1, allowing us to analyze the conditional probabilities related to gearbox types for each fuel type. Let's interpret the output based on the conditional probabilities. For CNG cars, the probability that the car has a manual gearbox is 1, indicating that all CNG cars in our dataset are equipped with manual gearboxes. For petrol cars, the probability of having a manual gearbox might be around 93%, showing a very high likelihood that petrol cars will have manual gearboxes. This perspective is particularly useful for understanding how gearbox preferences or configurations might depend on the type of fuel used. For example, the strong association of manual gearboxes with CNG could be due to specific market demands or manufacturing strategies. Similarly, the high prevalence of manual gearboxes among petrol cars could reflect broader consumer preferences or cost considerations. By examining the data through both row and column, we gain a fuller understanding of how two categorical variables, gearbox type and fuel type, interact within our dataset. These insights can guide strategic decisions in automotive design and marketing, enhancing the relevance and impact of product offerings. Now, let's shift our focus from categorical variables to understanding the relationship between numerical variables using correlation. Correlation is a statistical measure that describes the strength and direction of a relationship between two numerical variables. When we talk about correlation, there are three types of correlation, such as positive correlation, as one variable increases, so does the other. For example, an increase in a car's weight typically corresponds to an increase in its price. Negative correlation, as one variable increases, the other decreases. For example, as the age of a car increases, its price tends to decrease. No correlation, there is no noticeable pattern in the changes between two variables. And the correlation values range from -1 to +1. Values close to +1 indicate a strong positive correlation. Values close to -1 indicate a strong negative correlation. A value of 0 indicates no correlation. And for visualizing correlation, scatter plots are used. Scatter plots are useful for visually identifying the type of correlation between two variables. A plot showing a clear upward trend indicates positive correlation, while a scattered plot with no clear pattern suggests little to no correlation. For calculating correlation in Python, we use the .corr method from pandas, typically on a data frame that only includes numerical data. Here's how you can filter out categorical variables and compute the correlation matrix. Since our data frame contains both numerical and categorical data, we will create a new variable called numerical data which stores only numerical data by excluding object data type. We will exclude object data type. And to compute the correlation matrix we will use .corr method, and the default method is Pearson. The correlation matrix provides the correlation coefficients between each pair of variables. Here's how to interpret some typical values. Diagonal values, which is also called as self-correlation, are always 1. A coefficient of -0.87 between car age and price indicates a strong negative correlation. As the car gets older, its price tends to decrease. A coefficient of 0.58 between car weight and price suggests a moderate positive correlation, heavier cars tend to be more expensive. And for exploring further, you might encounter different scenarios where other correlation measures are more appropriate. Like, Spearman's rank correlation is used when data is not normally distributed or when dealing with ordinal variables. And Kendall's tau is another rank-based correlation measure, often used for smaller datasets or with many tied ranks. This understanding of correlation not only aids in identifying relationships between variables but also in forecasting and modeling decisions, especially when determining which features might influence a target variable like car price. As we wrap up this session, you should now have a solid foundation in both the visual and numerical methods for assessing correlations in your data. Let us now wrap up with a summary of what we've covered in this lecture. We started by creating frequency tables to examine the distribution of each category within a categorical variable. This helps us get a clear initial picture of our data's categorical composition. Next, we explored the relationships between two categorical variables using two-way tables. These tables provide a foundational look at how different categories interact. We shifted focus to numerical variables to check the strength and direction of their relationships through correlation. Using correlation coefficients, we identified whether pairs of variables moved together, positive correlation, in opposite directions, negative correlation, or showed no noticeable pattern or no correlation. We hope that this lecture helped you in understanding of the data and equips you with the analytical tools to conduct thorough exploratory data analysis. Thank you for your attention, and we hope this session has provided you with valuable insights into the fascinating world of data analysis.